Hello, everybody. Today we're going to be focusing on balancing equations. So we're starting a new chapter. First, we're going to look at some of the basics of equations and then get into the balancing. So let's go ahead and get started. Remember from back in chapter 2, we talked about the law of conservation of matter. It stated that in a chemical or physical reaction, matter cannot be created or destroyed, only changed from one form to another. Therefore, according to the law of conservation of matter, the number of atoms on the reactant side must equal the number of atoms on the product side. This is why we have to balance equations, to keep the same amount of atoms on the reactant side as the product side. So how do we know a chemical reaction has occurred? Back in chapter 2, we looked at these 4 indicators. First one we stated is that there could be a color change. There could be a precipitate produced in solution. Remember, a precipitate is a solid formed from the reaction of 2 aqueous solutions. There is an odor or a gas produced. And the last indicator is light or energy is involved in the reaction. So some sort of energy change, temperature change, or light given off. There's many symbols used in chemical equations, so we're going to look at what those symbols are. The plus sign is used to separate either 2 reactants or 2 products. The arrow means yields or separates the reactants from the products. Hide that there. The double-sided arrow means that we have a reversible reaction. The little s is a solid. The little L is a liquid. The little G is a gas. And the little AQ is meaning that it is aqueous or dissolved in water. The other arrows that you see there, you see the triangle over the arrow or heat written over the arrow. That means that heat must be added for the reaction to occur. And then when you have PT written over the arrow, that means a catalyst has been added to the reaction. PT is platinum. Platinum is often used as a catalyst in many chemical reactions, like the catalytic converter that you have in your car. That also acts, the platinum in the catalytic converter acts as a catalyst with the exhaust of your car as well. All right, so make sure that you review and know those symbols that are used in chemical equations. The reversible reaction we will get into a lot. We have an entire chapter about reversible reactions with chapter 18. So we'll definitely talk about that concept more then. All right, so here we see a chemical equation or a chemical reaction written out. We have 1 glucose molecule plus 6 oxygen molecules yielding or turning into 6 water molecules and 6 carbon dioxide molecules. So let's talk about what those things mean there. So here we see the plus signs. So we said our reactants or our products are always going to be separated by the plus signs. We see the arrow between our reactants and products. That means to yield. So it separates our products from our reactants. Reactants are on the left and your products are on the right. That is essential information. You need to know reactants are on the left, products are on the right. Guarantee you will be seeing that over and over and over again. The number in the front of the chemical formulas are called coefficients. The purpose of a coefficient is to indicate how many of each of the substances are present. So I mentioned this in the beginning of the slide, but we're also going to see it again. So there is 1 glucose or C6H12O6 molecule. There are 6 oxygen molecules represented here, 6 water molecules, and 6 carbon dioxide molecules represented here. So finding the number of atoms. So we are seeing chemical formulas and we are seeing coefficients. How do those work together? Well, you're going to multiply the coefficient by the subscript to determine the number of atoms in a chemical equation. So in this chemical equation, for example, We could ask the question like, how many atoms of carbon are on the product side of the equation? Or how many atoms of hydrogen are there on the reactant side of the equation? Or how many atoms of oxygen are on the product side of the equation? This is one of those ideas that it's easier to show you than to just do on slides. So I'm going to go to our notes. And we're going to look at this idea together here. So how many atoms of carbon are on the product side of the equation? So products we know are on the right and reactants are on the left. So what I would do is I'd find carbon, and I have the coefficient here of 6. There's no subscript written after carbon, so we can assume that's a 1. So 6 times 1 would be 6. So our answer is 6 carbons. How many atoms of hydrogen are on the reactant side? So now I'm going to go to the left-hand side. Here, there is no coefficient written. We can understand it is a 1 then. 1s, again, whether they're coefficients or subscripts, do not have to be written in a chemical equation. We would take that coefficient of 1, multiply it by 12, and we have 12 hydrogens. How many atoms of oxygen are on the product side of the equation? So now when we're looking at the products here, so we are looking on the right, and we are going to be looking at how many oxygens. Now, oxygens are in 2 different places, so I'm going to have to add those up. I have them in water, so I have 6 times 1 there. And I also have it in carbon dioxide. Here I have 6 times 2 oxygens there, which is 12. So 6 plus 12 is going to give me a total of 18 oxygen atoms. All right, so now that we know the basics of balancing equations, let's look at how to actually go and balance. When we balance equations, and especially in the beginning as you're starting to learn, it is helpful to fill out a reactants and products chart. So the reactants products chart looks like a T-chart, R on the left, P on the right, for reactants and products, and then we would write down how many of each substance we have to begin with. So on my reactant side, I have 1 sulfur, and then I have 2 plus 2 for a total of 4 oxygens. On my product side, I have 1 sulfur and 3 oxygens. So in looking at this, my sulfurs match, but my oxygens don't. One of the things you may notice on the reactant side there is that we have O2 and O2, SO2 and then O2. No matter what coefficient I put in front of there, it is going to give me an even number of oxygens on my left-hand side. So I want to get to an even number of oxygens on my product side. Sometimes we have to play with it to figure out like what number goes there, but it's always kind of good to just start with the lowest number to make it even. So the lowest number to make this even, I would put in a coefficient of 2. When I do that, my sulfurs change. I now have 2 sulfurs. My oxygens here also change. 2 times 3 gives me a total of 6 oxygens. So now on my reactant sides, neither sulfur nor oxygens match. So to get my sulfurs to match now, I would put a 2 in front of SO2. So that now gives me 2 sulfurs. But I have 2 times 2 or 4 oxygens plus 2 oxygens from right there for a total of 6 oxygens now. Now I am balanced. I have 2 sulfurs and 6 oxygens on each side of my reaction. You could either leave the blank in front of O2 blank. It's going to be an understood 1, or you can write a 1. It is completely up to you. Either way would be appropriate. All right, our next problem there, we see a polyatomic ion. Remember, polyatomic ions are ions that have more than 1 atom to it. And we see that with hydroxide, OH. Okay? When you have a polyatomic ion and it is the same on both sides, you can treat it as a single unit. It will make it much easier for you when you are balancing. So let me explain what I'm talking about. We have 1 iron there on the reactant side, 3 chlorines, 1 sodium, and we have just 1 hydroxide. The only way I have more than one is if it's in parentheses. So no parentheses means that I have just one of them. Over on my product side, I have 1 iron. And here I have 3 hydroxides because it has parentheses around it. So 3 OHs. And when I write these in my reactants products chart, I'm going to write them next to each other because it makes it much easier for comparison. And then I have 1 sodium and I have 1 chlorine. Now, whenever you have polyatomic ions in your equation, you're going to want to balance those first because they help everything else balance out. So I have 3 hydroxides and 1 hydroxide. I am going to put a 3 then in front of sodium hydroxide here. That now gives me 3 sodiums and 3 OHs. So this has changed to 3 and this has changed to 3. So then now that the polyatomics match, I would look at everything else. Irons match, chlorines do not, sodiums do not, hydroxides match. So I have 3 chlorides, 3 sodiums. On my product side then, in front of sodium chloride, I can put a coefficient of 3. That now means my chlorines match and my sodiums match. So everything is balanced. Again, in front of the iron 3 chloride and the iron 3 hydroxide, you can either leave it blank or you could put a 1. Either way would be appropriate. All right, in the next reaction, it looks pretty complex, but it's actually a pretty simple reaction to balance. We see a couple of different rules here. One of them is the polyatomic idea. So we see ammonium here and here, so we can treat that as a single unit. We see phosphate here and here, so we can treat that one as a single unit as well. We also see carbonate, CO3. It's here and here, so we can treat that as a single unit. So when I'm writing out my reactants and my products chart, we're going to treat those as single units. So for the first one there, for ammonium, notice you have parentheses and then the subscript of 3. That indicates that you have 3 ammoniums in that reaction. Now you also have PO4. Since it has no parentheses around it, that means you just have 1 of them. And then next you have a subscript of 2 after aluminum, so you have 2 aluminum atoms. And then you have a subscript of 3 outside of the parentheses of carbonate. Since I have parentheses around it, that means I have more than 1 of them, and that subscript of 3 indicates that I have 3 of them. So now we're going to go to our product side. You have parentheses around ammonium again with a subscript of 2, which means you have 2 ammoniums. No parentheses around carbonate here, which means I just have 1 of them, so 1 CO3. In AlPO4 there, I have 1 aluminum. No parentheses around PO4 or phosphate, which means I just have 1 of those. So we said you would want to balance polyatomics first, so we might as well start with the ammoniums, the ones on top there. Notice how we have the 3 and the 2, okay? So we have the 3 and the 2 there. We would have to find a common number between 3 and 2, and you're going to see this in many of your problems. So whenever you have a coefficient of 2 and 3, the lowest common number between them is 6. So you're going to have to make them both 6. So I'm going to put a 2 in front of ammonium phosphate. That will now give me 6 ammoniums there, and it also gives me 2 phosphates. On my product side, I'm going to put a coefficient of 3 there because 3 times 2 is 6, so that gives me 6 ammoniums. And now I have 3 times 1 carbonate, which makes this 3. which is great because I had 3 carbonates on the left. Now I also have 3 carbonates on the right. So looking at my reactants products chart, ammoniums match. I have 2 phosphate, 1 phosphate, 2 aluminums, 1 aluminum, 3 carbonates, 3 carbonates. So the only things that do not match are aluminum and phosphates. On the reactant side, I have 2 phosphates, 2 aluminums. So I'm going to put a coefficient of 2 here to now give me 2 phosphates and 2 aluminums. And now I am balanced. And again, if you choose to, you may put a 1 in front of the aluminum carbonate. All right, so we went over most of the rules with these first 3 problems. This 4th problem follows special rules. This is an example of a combustion reaction, a hydrocarbon combustion. C2H6 is considered to be a hydrocarbon. It contains carbon and hydrogen compound. It is combustion because it's reacting with oxygen, and you're making carbon dioxide and water. So whenever you have a hydrocarbon combustion reaction, you are going to start off the same way. You are going to balance your carbons first, then balance your hydrogens, and then add up your oxygens. So we don't need a reactants products chart for this problem. Okay, we're going to do it a little bit differently. So we're going to balance carbons first. So notice I have 2 carbons there. And that means I'm going to put a 2 in front of carbon dioxide. That now gives me 2 carbons there. Then we balance hydrogens. So I have 6 hydrogens on the left. I'm going to put a 3 in front of the water. 3 times 2 is 6. So that now gives me 6 hydrogens there. Then we add up our oxygens. So I'm going to add up my oxygens. So here I have 2 times 2, which is 4 oxygens. 3 times 1, which is 3 oxygens. 4 plus 3 is 7. Well, to get 7 oxygens here, I would need a decimal value. I would need 3.5. Now, you cannot have decimal values in your answers. So to get rid of the 3.5 you would need there, what I end up having to do is going and doubling everything in the reaction. And then whatever this odd number is here, that's going to become my coefficient in the problem. Okay, so let me explain what I'm doing. So we assumed that this guy was a 1 before, the C2H6. So now I'm going to double it from 1 to 2. The 2, I'm going to double to a 4. The 3, I'm going to double to a 6. And the odd number becomes my coefficient in front of O2. And then I could go back and double check my work. So if we look at my calculations here, we have 2 times 2, 4 carbons, 2 times 6, 12 hydrogens, 7 times 2, 14 oxygens. On my product side, I now have 4 times 1, 4 carbons, 4 times 2, 8 oxygens, but remember they're in 2 places, 6 times 2, 12 hydrogens, and 6 times 1, 6 oxygens. So carbons now match, hydrogens match, and I have 14 oxygens. 8 plus 6 is 14 oxygens. They match. So let's just kind of review what I talked about with that hydrocarbon problem, okay? Balance carbons first, then balance hydrogens, then add up your oxygens. If your oxygens are even, you can answer the problem. You can put a coefficient in front of O2 then. However, if your oxygens are odd, like they were here, you have to double all the other coefficients, and then the odd number will go in front of the O2. That method will work every single time. All right, so that's it for our basics for balancing equations for today. Make sure you've taken good notes, and you're going to do balancing equations day 1 for homework.